Good morning, everyone. Today we'll be covering the second topic of our vector calculus, that is the divergence of vector. And the third topic of the curl of vector will be included in the third video of the vector calculus topic. So the first one is the divergence of function. The mathematical explanation for the divergence of function is that we have to calculate the dot product of del into function f, where f be some vector function written in the form of f1 I cap plus f2 j cap plus f3 k cap. And del is the operator, partial derivative operator, that is the partial derivative of x into I cap, the partial derivative of y into j cap, plus the partial derivative of z into k cap. So we'll be substituting these two values in the equation, that is del dot f. For del, we have the partial derivative of x plus the partial derivative of y plus the partial derivative of z into k cap dot your function, vector function, that is f1 I cap plus f2 j cap plus f3 k cap. So for the dot product, we only take for the case of I dot I or j dot j or k dot k. But I dot j or j dot k is equal to 0. Why? Because when we are taking the dot product of two vectors, that is, let us suppose that A and B be two vectors, then the dot product of these two vectors will be AB cos theta. And for these vectors, ij or jk, the angle formed between them is 90°. Therefore, the dot product of these two vectors will be equal to 0. That is the reason we are only taking I dot I, j dot j, or k dot k only. So the dot product of these two vectors will be partial derivative of f1 with respect to x, the partial derivative of f2 with respect to y, the partial derivative of f3 with respect to z. In this manner, we can calculate the divergence of function. The physical interpretation of this function can be taken for the case of fluid. Let us suppose that our fluid is moving in a three-dimensional plane, that is x, y, and z. Let us consider a small parallelepiped cube on the fluid such that its one side is parallel to x-axis will be taken as dx, parallel to y-axis will be taken as dy, and parallel to z-axis will be taken as dz. And this fluid is flowing with the velocity v, that is Vx along x-axis, Vy along y-axis, and Vz along z-axis. Fine. So let us assume for the first case that our liquid is flowing along the x-axis and it is entering this cuboid with Vx velocity through the face of A, B, C, and D, and exiting this cuboid with the face of PQRS and the with velocity Vx plus dx. So the mass of fluid per unit time through ABCD phase can be calculated by multiplying the velocity component to the area of that phase. Fine. So the velocity component is Vx and the area is dy into dz. Similarly, mass of fluid per unit time through PQRS will be obtained again by multiplying the velocity component into the area. And this velocity component can be expanded with the help of your Taylor series, which states that this will be equal. We are expanding it using Taylor's theorem. Fine. So the decrease in mass per unit time can be calculated by subtracting your mass through ABCD minus the mass through PQRS. Sorry, why I'm not able to. dy I'm not able to write it. dy into dz minus del over del x vx dx dy dz. So this component will cancel out and we will be only left with the negative of vx dx dx dy dz. This negative sign is indicating the loss of mass and nothing else. So the mass decrease in mass per unit volume can be calculated by dividing this component, that is dx dy dz, by the volume of the parallelopipe we have considered, that is this. So this component will cancel out and we will be left with this is along x-axis. Similarly, along y-axis it will be del vy over del y, and along z-axis it will be del vz along del z. So let us consider this equation 1, 2 and 3. So the total loss will be calculated by adding first, second and third equation. It will be del Vx over del x plus del Vy over del y plus del Vz over del z. We can write it in the form of operators, dot product of operators, that is del over del y j cap plus del over del z k cap into Vx I cap plus Vy j cap plus Vz k cap. So we can write it in the form of del dot. So this is the physical interpretation of the divergence. Now we will be solving one question with the help of the example 1, in which we have to find out the divergence of this vector. Again, we'll be taking the dot product of del dot this vector, that is del dot v. So del dot v, again we'll be taking your del vector, that is del over del x I cap, del over del y j cap plus del over del z k cap dot this vector, that is x I cap plus y j cap plus z k cap over root of x square plus y square plus z square. It will be del over del x whole upon x square plus y square plus z square plus del over del y, again the y component, that is y upon x square plus y square plus z square, and the z component, it will be z upon root of x square plus y square plus z square. So when we are taking the partial derivative of with respect to some vector, then only that vector will be considered as variable. Except that vector, every variable will be considered constant. Like in our first case, the variable considered will be only x. Y and z will be considered as constant. So we'll be differentiating it. Numerator differentiation, denominator as it is, minus denominator differentiation, numerator as it is, whole upon x square plus y square plus z square. Similarly, we'll be calculating it for the case of your y component. It will be this minus y square x square plus y square plus z square raised to power minus half whole upon x square plus y square plus z square. And the z component, it will be root of x square plus y square plus z square minus z square x square plus y square plus z square raised to power minus half whole upon x square plus y square plus z square. Then in continuation we have x square plus y square plus z square minus x square whole upon x square plus y square plus z square raised to power 3 by 2. Similarly, x square plus y square plus z square minus y square for y component, and denominator will be same. Similarly, x square plus y square plus z square minus z square whole upon x square plus y square plus z square raised to power 3 by 2. So x square will cancel out, y square will cancel out, z square will cancel out, and you will be left with twice of x square plus y square plus z square whole upon x square plus y square plus z square raised to power 3 by 2. It is twice of root of x square plus y square plus z square. So this will be the solution or the divergence of the given function, and similarly we can calculate the divergence of other functions using the same procedure. And here we cover our topic of divergence for vectors. Thank you.